Hello and welcome to the Ask Me Anything About Empower 3 live webinar. This is the fourth webinar for 2019, so thank you for joining us. Today's topic is peak purity, and I just want to remind all of you that in the blog, which can be found at www.waters.com/empowertips, please go to see tips 134 through 138, as those tips do cover peak purity using the photodiode array detector and Empower. Let's take care of a few housekeeping things. First of all, the agenda. I do have some introductory notes that I will go through. We did receive questions during the registration process for today's event, so thank you in advance for the very good questions, and there was some commonality in some of the questions as well. And we'll go through a select group of those questions, and then we'll go to live Q&A, where I'll answer the questions live in Empower, and then we'll have a little summary, and we'll wrap up for today. So if you have a question, if you want to submit a question during the webinar, use the Q&A feature. We're obviously limited in time, so we'll get to as many questions as possible. One of the things that I will do is, since we have your registration information with your email, any questions that I don't get to, I'll send you an email. So that's the way we'll handle that, because obviously in an hour we can't get to everything. And on conclusion, you'll also get an email with a link to the recorded webinar and a slide deck with all of the things that you'll be seeing here today. I think most of you follow the blog and know who I am. I'm Neil Lander with Waters. And last month in November, I celebrated my 25th anniversary with the company. I've had a variety of different roles here at Waters. In the last 5 years, I've worked in the informatics group, and I do focus, as I think you all know, on Empower, both internal and external support for our Empower chromatography data system. Now, before we get started, I'd like to mention, and it's never too early to mention, that we have our Inform 2020 meeting coming up in mid-May. It'll be held in Rome, and some of you, I'm sure, have attended. Some may have not attended before. I think it's a great opportunity, yes, to meet me and ask me questions in person, but also we are organizing a number of workshops and tutorials, hands-on tutorials around Empower. So there'll be a lot of focus on Empower at Inform, as always. So I think if you can make it, it's great. There's information on the screen here, waters.com/inform. You can send me an email if you're not certain about something. I'll be happy to help you out with it. I'll be there doing a number of sessions, and it also gives you the opportunity to meet people in the industry that may have similar questions or doing similar work, and you can certainly collaborate and share information. Now that we did that, let's get to our first question. So I had this question more than once during the registration process, no surprise. Could you please provide an overview of peak purity? And a few of you sent this question in slightly different formats, but essentially the same thing. What do we really mean by peak purity? And there may be a slight delay in the slides as I advance them, so I'm going to try to be cognizant of that. So what we're talking about when we talk about peak purity is a peak, a chromatographic peak, spectrally pure? We're not talking about chemical purity. We're talking about spectral purity. And what does that really mean? So what we are doing is, and Empower is doing it mathematically, but in plain terms, you have across a chromatographic peak a number of spectra. And the number of spectra depends on a couple of things, which I will address in just a moment. And what we're doing is we're taking all of those spectra across that chromatographic peak, and we want to see if those spectra are essentially the same. So if we were to overlay the spectra and normalize them, so removing the concentration differences, just looking at the shape differences in the spectra across the peak, if I normalize and overlay, do they overlay, or are there differences when we overlay? Because if there are differences, then we have an impurity, or maybe more than one impurity, under that chromatographic peak. So basically, again, peak purity is really spectral purity or spectral homogeneity, if you will, looking and comparing the spectra across a chromatographic peak to make sure they're the same. This is not chemical purity. So if you're looking for an impurity, does the impurity absorb at the wavelength range over which you're collecting data with your photodiode array detector? Is the impurity there in sufficient quantity? Is the impurity sufficiently different spectrally from the main component that you're looking at? So all of these factors will affect whether or not you will be able to pick up that there is an impurity somewhere underneath your chromatographic peak. Now, I put this question in for the audience. This was not part of the question that I received. If I have perfect coelution of a main component and an impurity, will Empower tell me that the peak is spectrally pure, yes or no? So I have perfect coelution of the main compound and an impurity. In this case, Empower will say that the peak is spectrally pure. Why? Because UV spectra are additive. So at every point across the peak, if I have perfect coelution, the spectra that I get will be the additive combination of the main component and the impurity. And since it's perfect coelution, all of those spectra across that peak will be exactly the same, and Empower will say that the peak is spectrally pure. So you might extrapolate that and ask another question, which would be, well, if I have perfect coelution, how would I know? Well, the way around that is if you can make a library, make a UV library of the spectra of the known compounds, then you can do both the peak purity checking and the library matching to see, number one, does the apex spectrum match the pure compound that you have in your library? So there are ways to work around that, but I think we need to be aware of that. Now, when we talk about spectra across a peak, what are we really talking about? If you look in your instrument method, you will set a sampling rate. How many spectra per second will we collect? Then we have our chromatogram, and we have the peak integrated. We have a start and a stop for the peak. So Empower calculates how many spectra you have across that peak. So it depends, again, on the sampling rate and the width of the peak at the baseline. And so you can see in this slide, hopefully, that a lot of these peaks have anywhere from 52 to 100 spectra across the peak. So when we say peak purity, again, what are we doing? We're taking all of the spectra across that peak, and there are quite a few of them, and we're comparing them. We're essentially overlaying them, normalizing them to determine are they all the same or are there differences. That's what we're talking about here. If you go to your instrument method, if you have a Waters photodiode array detector, if you take a look and you go into the online help by pressing F1, there's a little table in there depending on which model of detector you have, and that table will help guide you in terms of what you should set the sampling rate to depending on the width of the peak that you might have. So I suggest taking a look at that. So great question. A number of you asked, you wanted to know what is peak purity, so thanks for that very good question. Another question which comes up quite often, and I'll read this one, what is the limitation in terms of spectral linearity issues when there is the necessity to dilute the sample? So this question comes up a lot in different forms, and those of you that have read the blog or have heard me speak on peak purity before, or any of my colleagues that make presentations or do Empower training will mention that you need to keep all of your peaks under 1 AU according to MaxPlot. And so you might ask, well, why is that important? First of all, just to make sure we all know what we're talking about, MaxPlot is a tool that we use for developing our processing method to do peak purity. MaxPlot is a two-dimensional chromatogram that plots each point in time at the highest absorbance across that collected wavelength range. So when we're collecting 3D data, we're collecting over a wavelength range, and so MaxPlot will plot each time point at its max absorbance across the wavelength range. And MaxPlot helps us do a few things. First of all, it's going to help us identify a small piece of the baseline that we can use for our noise interval. And secondly, it's going to show us for our peaks. Are the peaks under 1 AU, yes or no? So that's another reason we use MaxPlot to develop our processing method. So why do we say we have to keep it under 1 AU? It's not a limitation of Empower. You can have peaks that are 2 AU, 3 AU in height. It'll calculate peak purity. So it's not a limitation of the software. But what happens is, if you think back to Beer's law, which is the relationship of concentration versus response, what will happen is at high absorbances, you get a combination of effects that will produce slight departures from Beer's law due to photometric error. And although from quantitation standpoint, if you were going to do a calibration curve and quantitate samples, this deviation has a very small effect on that. However, it can lead to distortion of the shape of the spectra at the very high concentrations. So in order to minimize these effects, we recommend that you keep the maximum absorbance according to MaxPlot of the compounds under 1 AU, or at least the compounds that you want to do peak purity for. So let me illustrate this in a slightly different way. And I'm going to apologize here because I have misspelled the word caffeine. So in one part of the slide it spells correctly, and on the left it isn't. My apologies. So if we take a look, if we ran a solution of caffeine at different concentrations through our UPLC or HPLC, and then we took the spectrum for the caffeine peak, and we overlay them, and we normalize them. Here, where we're under 1 AU, you can see they overlay beautifully. It's a little subjective, yes, but we normalize them, and you can see there's no shape difference across that across that concentration range. But the next slide shows if I go up to 3 AU and then I overlay and normalize, you can see on the right side of this slide that these spectra for caffeine do not overlay very well. There are some visual differences that you can see. And this is the problem. So if you can imagine Empower trying to calculate the differences between spectra, and even though this is the same solution of caffeine at different concentrations, Empower would think these are different compounds, and if these were spectra across a peak, it would say the peak is not pure. You can also see there's going to be a shift in lambda max. So that's the problem. You have to make sure that we keep the peaks under 1 AU according to MaxPlot to adequately do peak purity. Again, the question comes up a lot. I've talked about it a lot. It's in the blog. Others have mentioned it as well. And I always get the question, well, why? And so now you know. Here's the next question, which is also an excellent question that I've had a number of times. Should we report purity plot results or purity flag results, because result is not the same sometimes for both the results? So number one, it's a very good question, and number two, it's a very good observation. So as we know, Empower calculates peak purity mathematically using the spectral contrast algorithm. Let me just go to a quick look at something here. So Empower is going to do a mathematical calculation, and it's going to report a purity angle and a purity threshold. And we say that if the purity angle is less than the purity threshold, the peak is spectrally pure. But we also recommend that you check the purity plot for the peak as well. And the two really do need to agree. And here's why, and here's an example in the slide that you're looking at. So here's a sample that was spiked with 0.5% of an impurity. And this is actually, again, a caffeine peak. We love to chromatograph caffeine for these examples. So here's a purity plot for caffeine, and here are the numbers. And you look at the purity angle, and it's less than the purity threshold. So you might think, oh, great, the peak is spectrally pure. But when you look at the purity plot, you can see in the tail end of the peak, the green line, which is the purity angles, across the peak is actually higher than the threshold at one point. So let's take a moment to understand why do we see this potential difference. The purity angle is the weighted average of all the spectral contrast angles across the chromatographic peak. So if you think back to the earlier question where we talked about the number of spectra that are compared across the peak, right? Let's say we had 30 spectra across a chromatographic peak. What Empower is going to do is it's going to take the apex spectrum, that's the reference point, and then it calculates the spectral contrast angle between the reference spectrum and every other spectrum across the peak, including itself. And then it takes the weighted average of those spectral contrast angles, and that weighted average is then reported as a purity angle, and it's weighted towards the higher absorbance. It does the same thing with the threshold angle, because for every spectral contrast angle, a threshold is calculated. And so again, it takes the weighted average of those threshold angles, and it reports that as a purity threshold. But when you look at the purity plot, what are you looking at? You're looking at the individual points across the peak. So you're looking at that purity angle versus purity threshold at every point across the peak. And it's a very sensitive technique because you can see in this case where we spiked this particular sample with the impurity, it shows up very clearly in the purity plot. So, in conclusion to an excellent question, I always check both. I would always take a look at the numbers and also take a look at the purity plot, make sure that the two agree. Good question. Let's move to our next question, and these are all questions that were submitted during the registration process. So here's another very good question. What's the meaning of purity threshold, and how can set the correct value of the purity threshold to have the correct peak purity calculation? Very good question. So as I mentioned in the last question, Empower uses what's called the spectral contrast algorithm, which was an algorithm that was developed here at Waters many years ago when we introduced our Millennium software. And essentially what that algorithm does is vector analysis. Now, I don't want to scare anybody with a lot of math. It's really quite simple. But what the vector analysis does is the following. It takes a spectrum and it converts it into a vector. And a vector has two properties. It has a direction, it has a length, or a magnitude. The direction of the spectrum is based on the shape of the spectrum. So the direction of the vector, I should say, is based on the shape of the spectrum. The length or the magnitude of the vector is based on the concentration. So if I wanted to compare two spectra using the spectral contrast algorithm, Empower would convert both of the spectra into vectors, and then it would calculate the angle between those vectors, and that's called a spectral contrast angle. Now, like any scientific measurement, there's a plus minus in the direction of the vector. So in other words, if you took a solution of a sample or a standard and you ran multiple injections 6 times, and in each case you wanted to calculate purity angles, you would see a plus minus from injection to injection. Perfectly normal. Any kind of scientific measurement you make, there's a plus minus. So the threshold angle is supposed to take care of that plus minus. And the threshold can be calculated in a number of ways. One of the things that you can see that on the slide here is that there's noise. There's noise from the detector. And so what we do here to set the noise portion of the threshold is, again, using MaxPlot. We look for a small piece of baseline that has no absorbance across that collected wavelength range. And so when we do that, we get just noise, and there's a way to check that you've picked a good noise interval. You can actually look at the noise spectrum. This is not to be confused with the ASTM calculation for short-term baseline noise. That's something different. Here what we're looking for is just an area where across that wavelength range you do not have any spectral absorbance. And so the threshold angle can be calculated just based on the noise, based on what we call solvent effects. We can do noise plus solvent, or we can do what's called auto threshold. So the auto threshold is a feature that was introduced some years ago for Empower to make it easier to do the solvent portion of the calculation. And you have to verify that the auto threshold is working. And if it's not working, you can do the solvent contribution. So you see where it says noise plus solvent, in parentheses it says noise plus constant. So the solvent angle, once that's set, that's a constant in the calculation of the threshold. The noise is going to be variable. And what you'll find is for very large peaks, tall peaks that have a high absorbance, you have a small noise threshold or a small noise angle. For very small peaks, you're going to get a very large noise contribution. So the noise contribution, as it turns out, is inversely proportional to that peak height. All right? So there is a way to do this, and we can talk more about that, absolutely, and it's mentioned in the blog as well. And just a quick screenshot from the processing method in Empower. And you can see in the lower left, that's where you would select how you want the threshold angle calculated there. And in the upper right, the noise interval is, again, a small section of the baseline that is selected for the noise contribution to that threshold angle. So, great question. That question has actually come up many times, so I'm glad that we had a chance to address that in some detail here. So now we'd like to go see what questions we have coming in. And let's see. My compound has the absorbance only in between 250 to 360. So can I select wavelength from 250 to 360 in the processing method to calculate peak purity? Very good question. So let me do a screen share here. I want to show you a couple of things in order to answer this question. First, I'm going to do this in two pieces, and hopefully everyone can see my screen. So first of all, here's the instrument method in Empower. And the three critical parameters for doing peak purity are here: the wavelength range, the resolution, and the sampling rate. Now, we talked a little bit about the sampling rate before. We want to make sure that we have a sufficient number of spectra across a chromatographic peak to do peak purity. And ideally, you want at least 20 spectra across the peak. Wavelength range. So I get that question a lot. So what wavelength range do I set in the instrument method? Well, it really depends. So I'm going to answer your question in two pieces here. Bear with me. One, you need to look at the mobile phase that you're using. So the wavelength start should be above the UV cutoff of your mobile phase, because otherwise all the light is absorbed by the mobile phase. And the technical definition for the UV cutoff is the wavelength at which you have 1 AU of absorbance. So you got to take into consideration, okay, what's in my mobile phase? If it's, water and acetonitrile, well, that's very clear to the UV all the way down. But if I'm using some kind of a buffer, or if I'm using, preserved THF, well, that's going to have a higher cutoff. So you got to make sure that you start that above the UV cutoff. And what about the N wavelength? The N wavelength should encompass where your compounds absorb. All right, so a lot of PDAs go up into the visible, but if I have compounds that don't absorb into the visible, no point in collecting data up there. So that's the instrument method portion. Okay, now bear with me. I'm going to stop my share for a moment, and I am going to show a different screen. So just be patient here. I am now going to show you a processing method. Okay, good. We want to make sure, because there's a little bit of a lag as I switch the screens. So here, this is where we set the wavelength range over which the spectral contrast angles will be calculated. So you can set this to whatever range you would like to. So if there's a reason that you want to go from 250 to 360, provided that you've collected beyond that range, you could certainly set that from 250 to 360. The key is when you develop the processing method and you look at MaxPlot, the third nice benefit of MaxPlot is you can see what the lambda max is for your different compounds. So you're going to get three things out of MaxPlot: noise interval, are my peaks less than 1 AU, and number three, what's the lambda max for my different compounds? So when you look at that, then you can make an intelligent decision and say, aha, now I'm going to set the wavelength range over which my spectral contrast angles will be calculated. Right? So great question. Thank you for that question. I'm glad that somebody asked that one. So now let's go see what we have for another question. And let's see if I can read my colleague's handwriting here. What does max impurity in the purity table mean? Oh, these are two different questions? Okay. So what does max... Oh, it's one question. Okay, sorry. It's a two-parter. What does max impurity in the purity table mean? What if my standard does not have a purity flag? Does it mean I have an impurity? Okay, so let me see if I can bring up a screen for this. So bear with me here. I'm going to switch to something that you probably will not be able to see, but I'm going to, where is it here? All right, just bear with me. I'm just going to go get another screen to show you. If I can't, well, we'll just do the best we can. Let me see here. All right. Let's go to the caffeine. We've got the caffeine. Okay, I don't see what I wanted to, but that's okay. I think I can answer the question without it. I'm looking for one thing. And I don't see what I want. Okay, I'll just answer the question. But now, let me go back to the screen share so you can see what I'm looking at. Sorry for the delay here. We want to make sure we have the right thing. Here we go. All right, so here is a purity plot. So what does max impurity in the purity table mean? Max impurity, which I know I'm not showing you right now, means the point across the peak where the spectrum is the most different from the apex spectrum. All right? Remember, your apex spectrum is your point of reference. That's usually the cleanest piece of the peak, unless you have, again, a perfect coelution. So your max impurity is the point across the peak where you've got the most different spectrum from your reference. And it says, what if my standard does not have a purity flag? Does it mean I have an impurity? No. If it has a purity flag, it means there's an impurity. So I know it's a little counterintuitive in that you see that flag and you think, oh, it means it's pure. No, it means there is an impurity, and it means that the angle is greater than the threshold and you have a problem. So actually, you don't want to have the flag for your pure standard. I hope that makes good sense. Thank you very much for that question. All right, let me take another question here. And I am going to stop sharing and switch to a different screen to answer this very good question. And that question is how to check peak purity by QDA. So I know a lot of you have a QDA mass detector connected in series with your photodiode array detector. And there's a question about, well, if I have the QDA, how can I calculate peak purity with the QDA? So let me answer that question because it's a really good question. So I'm going to share an appropriate screen here. So again, bear with me for just a minute. All right. So hopefully you'll be able to see what I'm now showing. I'm now showing what's called a mass analysis window, which is within review. So if I have a photodiode array detector and a QDA mass detector connected in series, or even if I have a split flow to the two of them, it doesn't matter. But I'm running both of them. I'm collecting data from both of them. I can, working from the UV chromatogram, I can go to the mass analysis window. And if you see at the top of the window, it says spectrum view. There's a purity view. So what that purity view does, and what it allows you to do, is it allows you to look at 3 spectra across the peak, on the leading edge, on the apex, and on the trailing edge. And while there's no calculation, as there is using the UV spectra with the PDA, pardon me, and the spectral contrast algorithm, this is more a qualitative judgment, where you look at those 3 spectra across the peak to see if they are similar or different, and you're looking at the masses there. A number of things will affect this. You know, where are you taking the spectra from? How is the integration set up on the peak? So if I'm taking a leading edge spectrum that's in the baseline, like you can see over on the far right, that purple spectrum for leading edge is very noisy. Well, that's because it's probably being taken from a baseline point, and it's not really representative of the compound. So you do need to take into consideration where is it taking the spectra. Again, it's a qualitative comparison of those 3 points. Another thing you could do is you could extract spectra in the spectrum review window, and you could look at many spectra across the peak to see once again if they match up. All right, very good question. Thank you very much. Let's see. Here is another question. Is taking the default settings for peak purity a good starting point? I'm not sure. In other words, would I need to justify changing the default settings and reporting peak purity? Well, that's an excellent question. And to answer that question, let me stop sharing. And let me go back and bring back on our screen share the processing method window, because that's what we really need to answer your very good question. Time-wise, we're doing well. Good. Okay. So repeating the question, is taking the default settings for peak purity a good starting point if I'm not sure? Well, yes and no. What I would do is the following. And this is going to be a little bit of a repeat of something I said before, but it's really critical. In order to determine the wavelength range over which you want to process, the noise interval over which you want to have the noise portion of your threshold calculated, what I recommend you do is derive MaxPlot for your chromatogram, integrate the peaks, and it will automatically show you the lambda max for each of your peaks and each of your compounds. So that'll give you an idea of how you should set the wavelength range for processing. Number 2, again, you want to make sure all the peaks are under 1 AU. And number three, what you want to do is you want to zoom in on the baseline, all the way across the baseline, to find an area in the max plot chromatogram that only has noise and not peaks. And based on that region, you then come in and set the noise interval. All right? So I don't remember now, I'd have to make a new method, but I don't think the default noise interval is a good one, especially for those of you doing fast chromatography. If you're doing UPLC, I think the default is set in such a way that you may already have a peak there. So in this case, with this method, because it's UPLC, I set the noise interval early in, away from my peaks of interest. So absolutely, you got to look for that. And then there is a way of checking to see if you've picked a good noise interval. The other thing is the active peak region percent is 100. That's the default. Most of the time, that'll work pretty well. The only thing is the following. If you've got a very noisy baseline, and if your peaks are not baseline separated, then you have to set it lower than 100, because what happens is Empower will calculate peak purity for a peak from peak start to peak end. So if my integration is a little sloppy, if you understand what I'm saying, Empower doesn't know. It says, okay, this is the start, this is the stop. I'll calculate peak purity for you. So you got to make sure the integration is done reasonably well. I know that's subjective. And again, you have to consider, are the peaks baseline separated? Are they fused? If they're fused, you can't leave the active region at 100% because no peak will be pure at that point. And in reality, you should adjust your chromatographic conditions to separate them. But even if they're separated, it could be you have a low signal to noise, and you've got a lot of noise, and so again, you may want to lower that active region less than 100 so that you get away from taking the spectra for the baseline. All right, so I would really, rather than just accepting the default parameters, I would make some intelligent decisions. Look at your max plot, see what the lambda max is for the peaks, look for an area where there's no peaks according to the baseline of the max plot chromatogram, set your noise interval, then you can enable the purity here. And again, this active peak region, you'll have to think about the chromatography and the separation. Now, the threshold criteria, there is a way to validate auto threshold. I would start with auto threshold. All right? So great. Thank you very much for that question. And I see another question, which I just basically answered. It says, what exactly is the active peak region and what effect does it have on peak purity results? So that's what we just talked about. Remembering and keeping in mind that it calculates peak purity from liftoff to touchdown. 100% is the default. If your peaks are well separated, you've got good signal to noise, and you have, and I know this is subjective, I apologize, if you have quote-unquote good integration, then you can leave it at 100%. I think for the most part, regardless of whether you're using the traditional algorithm or the ApexTrek algorithm, if you follow our recommended way of setting peak widths and thresholds and so forth, you should have reasonable integration. I say that, and I also say to anybody that writes me, look at your own SOP, because you have to set up your integration according to the SOP that you're following in your laboratory, unless you're in an R&D environment, which obviously is a little bit different. Okay? There's another question. What's the variable corrective factor? How it must be determined? The auto threshold. Okay, yes. So what happens here is the following. I don't know if I have a screen open that I can show you, but we'll just look at this screen since this is where it's set. So you saw earlier in the slide that the threshold criteria can be noise only, solvent only, noise and solvent, or auto threshold. Okay, the noise should be determined from the baseline of the max plot chromatogram. That's a given. So the auto threshold The person that developed all of the algorithms, the gentleman that developed the spectral contrast algorithm many years ago, at some point he built in this auto threshold. What essentially happens is, in the background, there is a lookup table. So based on the absorbance of your peak, it will look up what an appropriate solvent angle should be for your threshold. Now, when we talk about solvent effects, we can be talking about things like, I made my mobile phase in the morning at 8 o'clock. I have trifluoroacetic acid, which is very volatile, and it's evaporating over time, and the mobile phase is changing. So there are a variety of solvent effects in the chromatography that we have to account for. So the auto threshold should automatically take care of that. However, you need to validate that auto threshold. How do you do that? What we recommend is take a standard at the highest working concentration, inject it 6 times, create a processing method to do peak purity, take into consideration all the things we've just talked about, set your wavelength range, your noise interval, enable purity, leave it on auto threshold, process the 6 injections. If in all 6 injections your purity angle is less than your purity threshold and all the purity plots look good, that tells you auto threshold is working. So you have to validate that. Now, what if in those 6 injections the purity angle is not less than the purity threshold? So then what you have to do, you don't have to re-inject anything, you're just going to reprocess the data. Set that threshold criteria to noise only, reprocess the data, and look at the purity angles. This is going to show you the variation in the purity angle from injection to injection that I talked about much earlier in this webcast. Take the highest value that Empower reports for a purity angle, come back to the processing method, set the threshold criteria to noise plus solvent, and where it says solvent angle, you plug that value in. And then you have a properly set threshold. Some people also prefer to look at the percent RSD for the purity angle rather than working with the threshold as much, because they know, plus or minus where our purity angle should fall for a pure peak based on a standard. Right? So it's a great question, and I really appreciate that question. Okay, we have more questions coming in. Good question. Thank you. Are low-level impurity peaks good candidates for peak purity? It depends, obviously, on what the chromophore is. I mean, if you're working at an appropriate wavelength range where it absorbs and you know what the lambda max is, it should be okay. But it's really going to depend on the compound. And I know sometimes I get the question, well, how low can I detect this thing with the photodiode array detector? I really can't give an answer to that because it's really going to depend on the chromophore and where is the lambda max and so forth and so on. Where we get into difficulties is if we have an impurity that has a lambda max that's very far down in the UV, and then you're working down in an area where there's a lot of noise or the mobile phase is absorbing, that's where we can get ourselves into a little bit of trouble or a little bit of difficulty. But if the lambda max is something reasonable, then you can do some experiments to see how far down you can go in terms of detecting. But absolutely, you should be able to do peak purity. If it's a well-separated peak, you should be able to do peak purity even on the very, very small peaks, such as impurity peaks. All right, so yes, I have other questions that have come in, and some of these questions are very similar to some of the ones we've had. But actually, this question that's coming in is a good one. It's a 2-parter that I got. How to validate auto threshold and noise plus solvent. We just talked about that. Detailed guidelines on peak purity parameters like wavelength range, noise range, and purity parameter, etc. So this is a broad question, which we talked about some of the things already. Again, with the auto threshold, I think it's important to validate that auto threshold as we talked about. But one of the things that we didn't talk about Let me stop sharing here for a moment because I'm going to show you a different screen. And actually, I have a PowerPoint slide that will help answer this question as well. Whoops. Hang on one second. Screen share. Let me go back to the instrument method. Okay. So let's go back to the instrument method here. This is important to discuss. Again, setting up, collecting data over the wavelength range, we talked about it. We talked about the sampling rate and the importance there, but one thing we didn't talk about is the resolution, and that's part of what this person is asking about here. So the resolution for a Waters photodiode array detector, we have a fixed slit width, and the resolution is in multiples of 1.2 nanometers, 1.2 being the default setting for this, and your optimum setting for peak purity, and also for doing any UV library matching. Why do I say that? Well, I say that because the lower the resolution setting here in your instrument method, the better the spectral resolution will be for the spectra of your compounds. All right, what do I mean by the spectral resolution? If you look at a UV spectrum of a series of data points that have been connected, right? We can say the same thing about our chromatographic peaks, right? We have a sampling rate, and we may bunch some of those points, but essentially a chromatographic peak is made up of a bunch of data points that have been connected. It looks like a smooth line in review. Same thing with the UV spectra, right? We're recording absorbances at different wavelengths, and then we're connecting the dots, or I should say IMPOWER is connecting the dots. Spectral resolution is the distance between two consecutive points on a spectrum. And the smaller that number, the more detail you will see in your UV spectra. Now let me show you something. And I'm going to stop sharing my IMPOWER screen, and I'm going to go, if you bear with me, I'm going to go get a slide that I use for these discussions. Hopefully you can see that slide now. And this is a great example, and those of you that have heard me talk on this before probably recognize. You're going to see the overlay of two spectra. They're both for benzene. The lower spectrum, which is in red, was collected with a resolution of 1.2 nanometers. And the upper spectrum, which is also benzene, was collected at 4.8 nanometers. And you can see they look very, very different. So what happens is 1.2 gives us the best spectral resolution. It gives us the smallest distance between consecutive points on the spectrum. What does that mean practically to you? That means it's going to give you the most descriptive UV spectrum you can get. When you choose something other than 1.2, and again, they're in multiples of 1.2, you will invoke what is called diode bunching or diode averaging. So you're averaging out the measurement, and you're essentially smoothing out a lot of the features in the spectrum. So when you look at these two, and I can tell you they're both the UV spectrum of benzene, they look entirely different. And also they can result in differences in lambda max. So when doing the instrument method, if you're going to do peak purity, if you're going to do library matching, make sure that the resolution in the instrument method is set to 1.2 nanometers to get the most information out of the UV spectra and to get what we call the best possible spectral resolution. So that is definitely something to keep in mind. Now, on the topic of sampling rate, which we talked about earlier, I have some other information that I'd like to share with you. Okay. Why is sampling rate so critical? Why is it so critical in general, not just for doing peak purity, but for doing chromatography in general, right? So if we undersample peaks, if we collect too few data points, then we will have our integration, our retention time calculations will be not reproducible because it doesn't have enough data points. If we have too many points, it can result in other problems. And I'm going to show you an illustration that will bring this point home to you, no pun intended. But you can see that if I sample on the far left at a very low sampling rate, I only have a few points to determine my peak. And you can see the upper point, which would be used to determine the retention time. From injection to injection, that might move, it might shift, and I'm going to get irreproducible retention times. And the area calculation can shift. And so I go to a slightly higher sampling rate. It's a little bit better, but still I'm missing some information. And so now when I get around 17 to 20 points per second, now I've got enough data points across the peak that I can reproducibly have Empower determine the retention time, calculate the area, calculate the height, and also if I'm doing peak purity, I now have a sufficient number of spectra across that chromatographic peak. There is a requirement to do peak purity in Empower. You must have a minimum of 12 spectra across a peak. And again, that's from liftoff to touchdown according to your integration. If you have less than 12 spectra across that peak, there will be an error. It won't calculate peak purity, and it will say to you in an error, insufficient peak spectra. And that's what it means. You don't have enough spectra across the peak to calculate peak purity. Same thing in the noise interval. When you choose a section of baseline for your noise interval, you need 12 spectra. And if you don't have at least 12 spectra in your range that you've selected, it will give you an error message that will say insufficient noise spectra. So these are some of the things we have to take a look at. Now today, with fast chromatography, if you saw earlier in my slide, my noise interval was only 0.1 minute, right? Which is 6 seconds. But I sampled at 20 points per second. So I've got 120 points in that little piece of baseline. So I've got more than enough spectra to do my noise interval. So if you're doing traditional chromatography, or I should say traditional HPLC, let's say, with 1 milliminute and a column with an ID of 4.6 millimeters, well, then your peaks are wider. You don't sample at such higher rate as you would on fast chromatography. But still, if I had a peak that was 30 seconds wide and I sampled at 1 or 2 points per second, I should have enough points across that peak to do my peak purity. So these are some of the things that you need to take into consideration. I have a slide here, hopefully. I don't know if you can see that. Hopefully you can. So in Spectrum Review, from the Spectrum Review pull-down menu, there's something that says Display Noise Spectrum. And you want to have a noise spectrum that's random in shape. So if you look at that black spectrum as compared to the red spectrum is the spectrum of the peak of interest, the one that's integrated in MaxPlot. And the black spectrum is the noise spectrum. And you see it's nice and random in shape? That's what you want. If you take a piece of baseline where there's absorbance, then your noise spectrum begins to have the same shape as one of your compounds. So if I take the noise interval from the tail of the peak, what do you think happens? Now the noise spectrum has a very similar shape, albeit it's noisy, but it has a similar shape to the spectrum for the peak of interest. This is a bad thing, because what will happen in this case is you will get a falsely high threshold, and then impure peaks will start passing. So you always, always, always want to pick the noise interval from MaxPlot, and then check it by going to Spectrum Review pull-down menu, Display Noise Spectrum. Make sure that the spectrum is random in shape and doesn't have a shape that's similar to the spectra of any of the other peaks that you have in your chromatogram. That is a critical point. So I'm glad we were able to mention it. We're running down on time. I know there are some other questions. So I think we are going to wrap things up. let me get to a summary here. First of all, Empower Tip of the Week can be found at www.waters.com/empowertips. You can subscribe to the blog, and what will happen is you'll receive an email every week with the complete tip. The advantage to that is you don't need to go back to the website to get the tip. You'll have it in your inbox, and you can read the full tip there. We also have the Waters Knowledge Base, which can be found at support.waters.com. The tips have been moved into that knowledge base, and that knowledge base is searchable. The blog is searchable too, but the knowledge base actually is better. The search algorithm is much better, and you'll be able to find the tips there as well related to a question that you might have. So I encourage you to check that out as well. Many of you have sent me questions directly through the blog, and I encourage you to continue to do that as well. We will also be scheduling the next Ask Me Anything About Empower webinar for the first quarter. We haven't picked a date yet, but we'll have a date, and then we'll advertise that once the date and the topic has been set. And to remind you again that we have Inform 2020 in Rome on May 11th through the 14th. I'll be there and look forward to meeting many of you that follow the blog. And again, it provides you with the opportunity to participate in workshops with people from the industry that you can get to know and share information with, and maybe help one another with different topics. And we do have hands-on tutorials with computers so that if you want to practice different things as we're doing today, whether it's peak purity or doing custom fields and so forth and so on, you'll have the opportunity to do that as well. All right. One last thing I'd like to mention. We do have educational services at Waters. So we offer training courses on a variety of topics around Empower. We do them in Waters offices around the world. We also have available to you the ability to come to your site to do customized, tailored training to your needs. And I wanted to mention that at least here in the U.S., there is a course. It's a one-day course called Using the Photodiode Array Detector with Empower Software. And we have already for the 2020 scheduled June 2nd in Morrisville, North Carolina, if you're interested. And I would encourage anyone worldwide to go to www.waters.com/training. And from there, you can check out the different training courses on Empower we offer. You can look at the geography, and you can look at the schedule as it becomes available. So we have reached the end of our time together. I'd like to thank you all for taking the time out of the busy day and the busy schedules as the year comes to a close, for joining us. We look forward to seeing you at the next Ask Me Anything webinar on Empower in the first quarter of 2020. Thank you so much. Have a wonderful day.